So we've seen a lot of ways that you can define a function, and the functions can be used to describe specific physical situations. But sometimes one formula isn't enough. Right? Sometimes one formula isn't enough to describe the situation that we're looking at. For example, let's say I'm sitting here at my desk in my office, and let's say I held this stylus in my hand out to the side. That's going to put it about 1 meter off the ground. And let's say I drop it. Right? If I do that, physics tells us that the height of the excuse me, that the height of the object is described by the formula or the function h of t equals negative 4.9 t squared plus 1, where h is in meters and t, that's the time, is in seconds. Okay, so let's see how this works. Let's see what this is telling us. How high will the object be after, let's say, 2 seconds? All right, well, if I evaluate this, remember how we do this with functions. I'm looking for h of 2, and that's negative 4.9 times 2 squared plus 1, which is negative 15.6 meters. Okay, when I let go of this pen, it is not going to crash through the floor and be about, give or take, 50 meters down into the ground, 50 feet down into the ground 2 seconds later. Okay, it's not what's going to happen. Right, what is going to happen is it's going to hit the ground, right? And let's see when it does that, right? How long does it take for it to get to the floor? Well, at the floor, the height is 0. So I want to solve the equation 0 equals negative 4.9 t squared plus 1. And let's see, we'll move the 4.9 t squared over, divide both sides by 4.9, and then take the square root of both sides, right? And if I do that, I get t is equal to 0.452 seconds, right? Less than half a second before that pen hits the ground. Okay, then what? What happens for values of t greater than 0.452? Well, the physics guys, they're perfectly okay with getting a negative answer. This is below the ground. Okay. Meanwhile, back here in the real world, things don't just fall through floors, right? I know that before 0.452 seconds, this formula is telling me what the height is. After 4.52 seconds, the pen has stopped moving. It's at the ground. It's just going to sit there. Right? So visually, if you come over to the graph over here, what's going to happen is at t equals 0, I'm going to do, this is going to be the t-axis. This will be the h-axis. At t equals 0, the object is 1 meter off the ground, right? This isn't any particular scale. I'm just going to sketch the graph. So after 1 second, it's here. Then it drops, and it hits the ground. So this would be t equals 0.452, and from then on, it stays on the ground. Okay, so now hopefully you're starting to kind of get an idea of what the problem is here. There's two functions going on here. This one, the curvy one here, is negative 4.9 t squared plus 1. This one down here is just 0. No, those are the h's, right? So h equals this, and then h equals 0. So to describe the position of this object here in the real world, I need two formulas, right? And that's where piecewise functions come in, right? This idea of a piecewise function, it's literally a function that is defined in more than one piece. So here's how I'm going to write this, right? I'm going to say my formula is negative 4.9 t t squared plus 1 when t is less than or equal to 0.452. And I'm going to say it's equal to 0 when t is greater than 0.452. And that is my new height function. Right? A function that describes the height in both circumstances. And this is an example. This is what we call a piecewise defined function. Right, now, if you're looking at this and you think about it for a minute, there's actually another little bit of a problem here. The way this function is defined, it allows for negative values of t. And that's not possible. Right? We can't go back in time. And again, the physics guys, they're fine with that. Yeah, what the heck? It's where the object was, or going backwards, or whatever. In our real world situation, we really don't want to allow this. So I could take this even a little further and make this 0 greater than or equal to t, less than or equal to t, less than or equal to 0.452. And now it really describes the behavior of this pen, starting from our initial possible point, t equals 0, all the way out as far as we want it to go. All right, so we've got another example here that's probably familiar to a lot of people. We have an employee getting paid, and he's getting $10 an hour, and the customary time and a half for working overtime. Okay, so hopefully right away you're seeing how we've got two different functions going on here. I have one function that's going to describe his regular pay rate, and I have another function that's going to describe his time and a half pay rate. All right, so let's think about this. To see what these two pieces of the functions are going to look like, it helps to look at some examples. Right, so first my question is, how much did he get paid for working 35 hours? Well, that's less than 40. So that's in the regular pay range. So for that many hours, you just take the number of hours and you multiply it by 10, and you get $350. So let's hold on to that, right? When the time worked is less than or equal to 40, the formula we use is 10 times t. Okay, what do we do when he makes more than 40? For example, what if he worked 42 hours? Okay, well, the way this works is he gets paid the base $10 an hour for the first 40 hours, plus what's time and a half on $10? That's an extra $5 an hour, so that'll be 15. But he only gets that 15 for the hours worked over 40. And I know you can just kind of look at that and say, okay, well, that's 2 hours, right? But I need you to stop and think for a minute about where that 2 came from, right? That 2 is the 42 hours minus the 40 hours that he already got paid for, right? So this is 400 plus 15 times 2 is 30. That's 430. All right, now this tells us how we're going to figure out our formula. The only number in this expression here that could change is the 42. Right? Maybe he worked 44, maybe he worked 41. All the other numbers stay the same. So for values of t greater than 40, he's going to make 10 times 40 plus 15 times t minus 40. And there, let's call it P for payroll, right? There is my piecewise defined payroll function. It's a little messy, right? We maybe want to clean this up a little bit. The 10t will just stay 10t. What's this bottom part? This is 400 plus 15t minus, what's 400 400 times 15, that's 600. Right? That's minus 200 plus 15t. And again, we've got these same ranges here. That is our payroll function. Now you might be asking, and it'd be a good question, why did I put the less than, or why did I put the equals on the first one up here instead of the second one? And that's, and from a practical question, that's an important thing to ask, right? In this case, try them both out. If you put 40 into the top formula, 10 times 40 is 400. And if you put 40 into the bottom formula, this is also 400. So it doesn't really matter, right? You're going to get the same number either way. And really that's what we're focused on, right? So I could have made it greater than or strictly less than up here, greater than or equal to down here. Doesn't matter in the end. You get the same thing either way. Okay, so in the next lecture, we're going to look at it. We're going to do a few more examples on this notation and making sure you're reading it correctly. Then we're going to talk about how to graph one of these piecewise defined functions.